Is it not? Hello, everyone. Welcome to the GSC 2026 uh, webinar series. My name is Rodney Hurt. I'm one of the GSC co-chairs this semester, and I'm glad that everyone is attending our seminar today. Before we get to Professor Shah's presentation, I'd like to introduce the GSC and let you know how you can reach us and who our team is. To start out, I'd like to introduce our GSC leadership team for this year. Myself and Zareen are the co-chairs. We have a great publicity team of Avinash, Ahmad, and Swapnil. Co-treasurers are Siavash and Anshu. And then we have a very big support team of Samuel, Roshan, Rachel, Saramya, Viva, and Naran. And then finally, our faculty advisor this year, every year, is Professor Farouk Mistry. With that, I would like to invite any graduate students, any students completely, to our leadership team meetings. We hold them this semester on Wednesdays at 6 p.m. And this time it's over Zoom. So if you'd like to attend and be part of our leadership team or just meet some of us, please send me an email and I'll make sure to get you that Zoom link. And then we update our meeting time every semester based on the schedules of all the leadership team and all the students who want to attend. So some years it's Wednesdays at 6, some years it's Fridays at 2 p.m., just whatever works best for all the team members. This next slide is really important for us. If you're not a member of the graduate student community on Engage already, please log into Engage. You can go to the link shown here, scan the QR code, and join the GSC. It helps us keep track of everyone so we can make sure you're aware of all the events that we have. It also helps us receive funding to show that our events are actually being attended, things like that. So if you like these webinars, other events that we host, please join on GSC so you know about it. Sorry, please join on Engage. Next up, we also have a LinkedIn page. We share all of our events on here as well. You can search just for graduate student community. You can go to this link on the screen here. It's also good for connecting with past members that might be working in academic jobs now or in industry. You may be able to make connections, for your own job search. Next up, Facebook and Instagram. Since not everyone has LinkedIn, most people have at least Facebook or Instagram. We also post our events on here. And at least on Facebook, you can see other members. You may be able to make connections that way. So you can scan the QR codes on the screen or search for graduate student community at OU. And then, please do join. Next up is our YouTube page. So thank you all for attending this webinar. But just so you know, if you've missed any past webinars or want to go back for more information, we post most of the webinars on our YouTube page. So you can go rewatch them there. You get contact information for the speakers from the post, anything like that. So you can scan the QR code here or just search for it in YouTube. Next up, I want to let everyone know about the Dave and Susan Burt team room in the engineering lab building. It's a nice space available for GSC members. If you need, just time away from your office or a quiet place on campus, there's a table in there to work on. There's couches, whiteboards, coffee pot, microwave. So you can email me if you need access to it, and I'll get everything coordinated. All right. Next up, once I finish the GSC introduction, I'm going to put a link in the chat for our attendance sheet. Please do fill this out once you see it in the chat. It helps us both keep track of people and maintain funding so that we can keep hosting events like this. So once it's in there, please fill it out. Second to last slide on here, I promise. I want to introduce some of the research frontiers for our seminar series this spring semester. So the research frontiers with generative AI. issues, methods, and applications. We know that generative AI is reshaping, everything, research, industry, society, like it says. But how can everyone be responsible with its use? So this spring, our seminar series has brought together, leading voices from industry, academia, CEOs, professors, all of that. Um, and then, we're always welcoming new speakers for future seminars. Um, Example topics could be how can people work with generative AI to create intellectual, economic, and social value, connect these domains. Another topic is research issues, methods, and applications that arise when people collaborate across research, industry, and community. And lastly, ways for people to design generative AI initiatives that link academic inquiry, economic innovation, and social benefit in ethical and equitable ways. All right. So if you or anyone you know would like to present on any of these topics, please let us know. We'd be happy to accommodate. A quick update, our final seminar of this semester, of this school year, will be next Wednesday when Dr. Generative will present on AI for fault detection and diagnosis in the domain of HVAC systems primarily. He's a postdoctoral researcher here at OU in the Building Energy Efficiency Lab. So I hope everyone will join for that. With that, I'd like to introduce Professor Shah. So Professor Shah completed his bachelor's, master's, and PhD at the University of Texas. Interestingly, his bachelor's was in mechanical engineering, and his master's and PhD were in electrical and computer engineering. Once graduating from the University of Texas, he held a variety of roles, but eventually became a professor at the University of Houston, where he founded the Quantitative Imaging Lab, working in video analytics, person re-identification, human motion, a wide variety of topics in that domain, and then became the chair of the School of Computer Science at the University of Houston. He joined OU last semester, the fall of 2025, is the director of the School of Computer Science, and has been named as OU's Chief AI Officer, where he's developing a strategy in AI innovation, research, education, and implementation, and will reimagine curriculum and academic opportunities to integrate AI across the student experience. Beyond that, he's a senior member of the National Academy of Inventors, senior member in IEEE, received the John C. Butler Teaching Excellence Award, and has over 200 publications in journals and multiple books. So with that, I'd like to offer the floor to Professor Shah to begin your talk.
Well, thank you so much. First and foremost, it's wonderful and truly a pleasure to be here. Let's see, can I share my screen?
Should be ready for you.
All right, does that work?
Perfect.
All right, excellent. Today I thought, I'll share a little bit about the research that we've been doing. And the idea of, or the problem of person re-identification. We've actually been working in this domain or in this problem for a long time. And I'll tell you a little bit in terms of how the problem has evolved, and more specifically talk about more recent work that we've been doing, and try to connect, sort of the generative AI elements into some of the work that we've been doing. Share a little bit of that. But before I go into that, I just wanted to kind of give a big shout out to a couple of the students who have always been engaged in this work, and a lot of the work that I'll be talking about today is really part of their PhD work as well as their postdoctoral research. So Dustin Wynn, sort of graduated with his PhD about a year and a half ago, and Pranav Mantini is a postdoctoral researcher at University of Houston, graduated with his PhD about 9 years ago, and has been working on this problem with me for this entire duration. So with that, let me share a little bit in terms of first outlining what the problem is. Right, so person identification is something that became a problem of interest ever since we started having sort of a broad capability and ubiquitous availability of being able to deploy cameras within the public domain, right? So you can imagine that in public spaces, we have a lot of cameras that are deployed. They are able to acquire videos, and most of the times those videos are stored for a temporary duration at some location. Depending on regulations and allowed laws, they might be just streaming the video and it's not actually stored. So it's moving through. But there are scenarios when these videos become very critical in terms of being able to understand what's happening in the environment. In the broader context of understanding what's happening in the environment, a subset of that includes the ability to identify people. Now, when I talk about identification of people, this is not related to biometrics per se, right? So we're not trying to associate a name with an individual, but we are simply trying to find an individual based on their general appearance in a viewed video and trying to identify if they've appeared somewhere else. So these kind of applications become extremely critical in search and rescue operations, or being able to identify a potential pathway a particular person may have taken in the broader geospace, and be able to leverage that information for a variety of applications, whether they are in search and rescue operations or potentially in forensic analysis. So what is the general person re-ID problem, right? So the general person re-ID problem sort of entails multiple steps. One is, of course, being able to have access to raw video footage, being able to identify, let's say, people or humans, right? In this case, we are talking about person re-identification. So being able to identify humans in the scene, which typically take the form of these little bounding boxes, the ones that I'm showing in red over here. And then essentially creating, if you will, a gallery of those observations. So multiple observations potentially of the same person as they're moving through that scene, and as well as potential observations of either the same or different individuals as they may have been observed across multiple cameras within the larger geospace. And a lot of times what that collection represents is what we call the gallery. Every once in a while, we might have either an observed input or an observed area of a person, which we use as a query. And essentially, the query translates to the question, have you seen this person before? And if so, where? And please identify that person. And that would mean that we would basically search this gallery in order to find that person. In other scenarios, the query may be an image coming from not an observed camera. It could be a separate image of a person, and we are trying to actually search through the gallery in order to identify if we have seen that person in that gallery or not, right? So that would be the search and rescue or potentially scenarios in forensics. So that's the general re-ID problem. And of course, in order to solve this problem, we essentially have to come up with a mechanism under which we learn what is it to represent an individual that we have observed in a camera or in an image, and encode that representation into our gallery, right? So in terms of machine models, we are talking about some kind of numerical representation that we have to encode, that we can leverage in order to come up with a equal representation of the query and everything that we have in the gallery, so we can actually compare the two numerically in order to create a match, right? So the general description is fairly simple. Now, so if I were to break this out into a system view of what this problem translates to, well, you have a query image, you have some kind of a learning model that is able to take that as an input and generate an output embedding, which is the numerical representation. We do the same thing from everything that's in the gallery. And then, of course, we have some mechanism to compare those two numerical representations. The comparison can be done in a variety of ways. The common ways to do this is by computing sort of a normalized Euclidean distance across the representations or potentially a cosine distance. And there are other ways that can be designed as well for doing this comparison, but these are probably by far the most common. And by computing these distances, we can then essentially create a rank ordering of every observation in the gallery against the query from the shortest distance to the largest distance. And that gives you a result or a mechanism to query and retrieve results from the gallery in some ordered fashion, really. So that's sort of the larger description of what the re-ID problem is. Now, obviously, as we think about this problem, we need to think about sort of the context in which we would like to have a solution available for solving this problem, and what are the real world challenges that we have to tackle, right? So one, when we think about the scenario, obviously, we're going to observe people in sort of in natural environments, and in that case, you might have different people that get captured in a video that look like they're wearing very similar clothing, right? So, I mean, just a simple example, right? Someone wearing a white T-shirt and a blue jean. Well, I mean, there can be a lot of people wearing, white shirts and blue jeans, right? So that's a fairly common occurrence, but doesn't mean that they're the same person. The other thing is, of course, the same person will over time be wearing different clothes. So if I observe someone today and I observe the same person tomorrow, well, there's a good chance that they have changed clothing, right? So it's the same person, but they will appear in multiple wearing appearances or multiple clothes. You also have a challenge because the observations that you capture or a camera captures are typically going to be from different viewpoints, right? People are going to be walking around or moving around in different angles with respect to the camera's observation viewpoint. So as a result, the captured data will have what we call viewpoint or pose variations. In addition to that, there are other situations, right? So occlusions, for example, there might be other objects. It's a three-dimensional space. So there might be other objects that basically cover up part of the observation or part of the person. You also might have illumination variations. So, your observations don't necessarily always happen at a fixed time through the day. You might have observations that might happen during the daytime versus nighttime. And as a result, it's going to have drastically different illumination problems. So these are some of the challenges that exist in the space. And in order to address that, we need to design appropriate methods and appropriate solutions. So what I'll talk about first is sort of trying to look at this from the standpoint of the scenario where a person appears, wearing different clothes, or of course, different people appear wearing similar clothes, and sort of the challenge of viewpoints, right? So viewpoint variations gets kind of interesting. So if you look at just the ability to observe the human shape, right? And if I were to say that one of the ways I can try to think of the human shape is by defining, let's say, a skeletal structure of the human body. And here would be an example of those skeletal structures, right? So a person like this, is just basically walking directly in the direction in the viewpoint of the camera. And of course, if I were to, draw the skeletal structure where, I can localize a few points on the face, I can localize the shoulders, the arms, and so on and so forth. That skeletal structure may look like this. Now, if I can come up with some representation to encode that as a numerical value, I may project that into some kind of a subspace. But if I notice a person that's actually walking, perpendicular to the viewing direction of the camera, their skeletal structure appears like this, but their numerical representation also projects quite close to this individual, right? So the shape itself, if I were to use skeletal representation as an encoding mechanism, may not necessarily allow me to differentiate these two or recognize that these two people are the same depending on the distance in terms of where they get their numerical representations project in a subspace. So I want to make sure that these presentations, either independent of their orientation of the body, tend to be close, while of course people who are different, independent of the shape representation, tend to be further away in my numerical representation. So we have to address this problem as well. So how do we try to come up with a generic way of encoding this kind of a solution. So of course, what I would like to do is have an input image, right? An observation of a person. Maybe I can separate out the encoding of um, how they appear, right? So their clothing and what we typically view as visual appearance. And I can also represent their body geometry as something that is invariant to the appearance, right? So the clothing, if you will. And if I can come up with a way to come up with numerical representations for either one of them, I can combine them in some way and come up with a common representation that I can then use in order to compare different images or different people images. So that is sort of the high level framework that we would like to build. Now, of course, as you can imagine, if I'm going to build this as some kind of a deep learning architecture or deep learning model, I will need lots of data to be able to do that. Now, one of the reasons this field of person re-identification has accelerated in the last few years in terms of its progress of achieving or solving these kind of challenges is because there have been a growing number of data sets that people have actually designed and developed and curated in order to further this kind of research, right? Because as I said, you'll need a lot of data. So, but there are obviously differences between different data sets that are available in order to pursue certain scientific or open research questions. So you have a few data sets here. One of the things to note is, each data set has different number of clothing variations per person that is in the gallery or in the data set. So in the LTCC data set, you might have people who are observed. Number of people is 152 in the data set. Those observations are from 12 different cameras, so give you an understanding of the different viewpoints. But the same person is appearing in the data set with maybe two possible different clothings observed or up to 14. On average, about 5 different clothing appearances per person. In the other data sets, again, it varies anywhere from an average of 3 to possibly 4. So there is no consistency in the number of appearance variations that exist among the people in any of these data sets. But nonetheless, that's a groundwork and a starting point for us to understand how we can build models that are more invariant to clothing variations, which is one of the fundamental problems in person reification. So we want to work towards that. One way of kind of thinking about that problem is, of course, collecting more data sets, right? But then we have to kind of structure those data sets so that we have larger number of occurrences of the same person wearing different clothes. Well, that can be done, but you can imagine that it's a fairly manual effort. It's a tedious effort of collecting and curating data sets. Or we can take an alternate approach is to actually come up with generative models that help us generate more observations of people, but in different clothing. So one thing that we actually tried was to design a GAN or a generative adversarial network in order to transfer the clothing of one ID, one person, over to another person, right? And we can actually do that, and that allows us to increase the number of observations per person with different clothing. Of course, part of that is being synthesized, if you will, right, by these generative adversarial networks, GAN models. Of course, by doing that, we could potentially are enhancing the robustness of the model that we actually learn by having more variations in our learning data set. And as a result, we would end up designing a method or an approach that is a bit more robust to clothing variations as well as viewpoint variations. So I'll talk a little bit about what that looks like and what that translates to in terms of potential results. So how do we actually do that? Well, what we did was, let's say you have an original group of observations of people. And of course, that will be in different poses, different viewpoints, if you will, as well as different clothing. Well, we take each one of them and we can extract what we call a typical appearance representation of the person. So in this case, we are taking two people. The first one, we can think of it as the source. the other one as the target, right? So what we would like to do is take this person's clothing and actually create a new image where this clothing is actually transferred to the target image, right? So what we learn is how to take an encoding that represents the clothing of each of these images. We also want to learn how to encode the shape representation of each of these input and target images. And then we want to actually pass the appearance of one and the shape of the other into a generative model or a GAN model in order to learn how to transfer the clothing from one to the other, right? So that's what the architecture is. And as a result, we can basically create an augmentation batch where we will have new synthesized images of the source clothing being transferred to a target image. So in order to do this, we actually use a simple ResNet model, right? So ResNet 50 is used to capture the appearance structure, which is the clothing. And what we build is a shape encoder, where the shape encoder is actually using a PoseNet, an ability to actually create the skeletal structure. And then we actually use an RGET model. So it's a recursive GAT model that we are using with a few different layers in order to capture that pose representation and come up with a vector representation that we can actually train a GAN model on for the clothing transfer. So that's what we do. The rest of the pipeline is mostly in terms of actually building a numerical representation that uses that synthesized data to come up with a more robust person-re-ID representation. So if you look at sort of the synthesis structure, what we are able to do then is there are some examples, right? So I can take an input image and say, this is the target image. And what we are able to do is take the visual clothing of this person and transfer it onto the original image, the input image. And as a result, now I will have the synthesized observation of this person with different clothing. Of course, different clothing is still constrained in terms of the different clothings I have available for different people in the same data set, right? So I can kind of do that. So again, here's another example of a person in a white shirt or t-shirt and sort of, I guess, gray shorts. Here's the target image where the person is wearing sort of this green t-shirt and some khaki trousers. But then we can generate and synthesize the image of this person, but appearing in the green shirt and khaki shorts, right? So this becomes a synthesized or a generated image that we have that we use to augment our data set. Now, once we augment the data set, we still need to learn off of the data set to come up with a representation for person re-identification. So what do we do there? Well, we basically introduce new loss structures in order to train the model. One is, of course, if I have now more synthesized images, remember, I want to be both appearance invariant as well as viewpoint invariant, right? So the training that we do is more specific. We try to basically do a hard triplet negative training or positive training or hard triplet loss. So you need to create positive examples and negative examples. And what we do is we actually take positive examples of the same ID, but with the synthesized additional appearance observations. And then we take all the other people who appear to have the same pose, but they are actually different IDs as negatives. Right? So this allows us to then explicitly encode a loss in the learning process that becomes more clothing aware loss. So we are going to be more agnostic to clothing.
I told him that the driver was from Pakistan.
Sorry, but Ron,
Well,
can you please
if we
mute
speak the
yourself?
same language.
Ron, can you
Let's
mute?
turn that
Yeah,
mute to people.
How was your stay there?
For
It was very helpful.
quiet.
Had a good time with.
Everybody that's not talking.
So I was very glad to meet you and know about Berbers.
Yeah.
You can
I
tell
think
me
it's Baron Pastakia.
this.
Baruch, you can mute with the host permissions.
Or you can
Who's
hear that.
who's the person?
Bam,
I
it's stuck here.
I can listen.
Barak, please mute yourself.
You can do it.
All right. So the
All right.
other loss is very similar, right? But it's more focused on viewpoint. So we kind of approach it the same way. But that loss is there so that we can actually train a model that becomes much more agnostic to viewpoints. So when we combine all of that, of course, we still are solving the person re-ID problem. So what we want is to be able to have a query image and actually get results back of the same person from the gallery, right? So same ID observations. Now, of course, we want to be able to quantify all of this. So there are typically, two different metrics we often measure in solving the person re-ID problem. One is the rank one accuracy, right? So rank one accuracy is nothing but when we create a ranked list of all the matches that we come up with, how often is the first match the correct match? That's really the measure of rank one accuracy. So if I end up with rank one accuracy of 80%, it means that, across all the queries, 80% of the times the obtained result, the first result I get is the correct result. The other thing is actually mean average precision, where the calculation depends on sort of a few different stages. So first, what is the precision? The precision is computed as the number of correct matches that are retrieved up to rank K, right? Where K can be basically anywhere from 1 to the number of images you have in the gallery. Of course, normalized by the number of retrieved samples for rank K, right? So basically, if I have a rank, let's say 1, I would, and I basically only retrieve one result from the gallery. And if the result is correct, then precision will be 1 divided by 1, 100%. If of course, the result is incorrect, the precision will be 0. I have only two choices. If it's 2, of course, I get the first match correct. Well, that's great. So that would be 1 divided by 2. And of course, I have to look at the second match as well in order to figure out. But, rank 1 precision would be 1 divided by 2, 50%. And of course, if I don't get the first one, then rank 2 precision would be 2 divided by 2 if I get it correct. So 100%. The average precision is actually the average of all the precisions across all ranks. And then the mean average precision is actually the mean of all those precisions across the entire gallery or entire query set, I'm sorry. So, if I'm, 100 query images, I'm basically computing the mean of the average precision for those 100 queries. So that's what the mean average precision is. The implication of that metric really is that if I have a high mean average precision, all that really means is that my model is able to retrieve correct matches early in the ranking process in solving that problem, right? So it doesn't mean that I'm unable to find the person I'm looking for, but the higher the mean average precision, the earlier they will show up in my rank ordered list. That's what it means. All right. So across some of these data sets, right, the LTSC, PRCC, deep change, these are data sets where you have a reasonable number of IDs in those data sets, and also you have number of people who are changing clothes. So there are two protocols in literature that people have designed around, sort of quantifying the implications or assessing methods for person re-identification. You have what is called a cloth changing protocol and a standard protocol. So the cloth changing protocol is where the query and the gallery images are set up in such a way that the same ID will always share different clothing. Okay. So basically you have different clothing in terms of the query and the gallery. The standard gallery is where if you have a query image, there is a likely image in the gallery of the same ID in the same clothing, but there will also be different clothing possible, right? So the standard protocol is targeting more in terms of saying, do I get a person match or not, even if they're wearing the same cloth is a possibility, right? So we're not testing how invariant we are to clothing representations, while the cloth changing protocol is stricter towards that, and it's focused on testing whether the model is robust to different clothing of the same ID or not, right? So you can kind of see that, there is an improvement by doing this kind of synthesis. I haven't discussed the results here, but what we found is that as we increase the number of different clothing for the same ID in our training data set, there is a gradual increase in number of clothing variations from 1 up to 6. After 6, if you have more variations of clothing for the same person, the model is not improving as much, right? So it's beginning to plateau out. Now, whether that generalizes well or not, that's something yet to be seen. But at least in terms of what we have observed, it seems to start plateauing out around that scenario. But overall, we definitely find by doing this kind of synthesis, the model is able to learn a little bit more better, and is robust, or its robustness increases. Now, beyond just looking at the clothing variations and viewpoint variations, one of the common occurrences that happen in the space is also occlusions, right? So observations of people where there might be something else that's occluding that observation, right? Could be another person or could be just an object. And you have scenarios like this. So if you have a query image like this, in the gallery, of course, these are images of the same person at different viewpoints. But in some cases, the observations are partial, right? Because they're overshadowed by something else in front of them. Similar example here. So how do we tackle that? Well, again, we need to kind of encode within our learning capabilities, our learning model, an ability to deal with these kind of observations. So first and foremost, right, if I were not explicitly modeling occlusion, what is my model learning, right? So that is sort of the first thing we wanted to ask. And one way to know that is to actually look at the attention maps once the model is learned, right? And if I look at the attention map, so let's say here's an image, right? And in building the numerical representation for this image, it seems that the model is learning to focus on all of these little, green and red areas. Red is a higher value, blue is a lower value. So red would imply I'm actually leveraging information from that spatial region in the image in order to come up with a numerical representation. And what we see is interesting, that it seems to encode a lot of information about the bag that is in front of this person. Similarly, in the case of this example, where I have a car in front of the person, it's actually pulling in quite a bit of information from the car, right? And obviously, that means that we are not capturing maybe possibly enough information about the actual person, right? So how do we change this behavior of learning that is happening in our architecture, in our deep learning models? Well, we can explicitly try to build a mechanism that is focusing on ignoring information that's occluded, okay? So how do we do that? Well, we can come up with sort of, in addition to our standard architecture, of encoding what we call occlusion type awareness. All right, so I'll talk a little bit about what that means. And remember, the objective is to focus on non-occluded regions in order to build our better and robust numerical representations. So one of the things that we kind of tried to simplify was think about the different kind of occlusions that can occur in our observation. So we imagine that maybe part of the upper body of the person can be occluded. In case the left upper body, right upper body can be occluded. Similarly, left or right lower body can be occluded. Maybe the entire face is occluded, or the upper body is occluded, or the lower body is occluded, and so on and so forth, right? So we came up with 8 different possible scenarios that we imagine could possibly be occlusion scenarios, right? Of course, there can be more. This is a simplified categorical, drill down of possible occlusion structures. Well, great. And if we have these 8, then we can synthesize this 8 occlusions simply by putting a black patch on standard observed imagery. And we can then build a simple classifier, if you will, in order to detect, given an input image, if any of the occlusions are present. So what we built was a very simple multi-layer architecture for what we call occlusion detection, which would basically come up with a label for any of these 8 occlusions, or of course, if nothing is occluded, there would be a 9th label to represent no occlusions. Okay? And we train this model separately by generating a synthesized data set of these possible occlusions. Once we have that, that model is frozen, right? So that's a very simple classification model. It's frozen. It generates a simple vector for the 9 or scenarios that can occur. Well, we still have our basic backbone structure for encoding the representation that we see in an image, right? This is exactly the same backbone that we talked about before. Remember, it produces a finalized vector that we use as numerical encoding. Well, we actually add the occlusion detection vector into that general architecture. So if you're building a standard CNN backbone, well, whatever the final layer of that backbone is, we simply add this occlusion type embedding vector and add it in. Now, how do we add it in? Well, we can either simply sum it in, we can concatenate or is that as a vector, or we can basically try to add one more layer of learning, which takes those 2 vectors and tries to actually drill it down into a single vector, right? So there are different ways we can actually, numerically or mathematically encode that vector in there. Interestingly enough, once we have that vector, well, we can use it for a transformer backbone as well. So imagine that we don't want to use a CNN architecture. We want to use a simple transformer, vision transformer, well, which is really patchwise encoding of the image. Well, I can take that occlusion vector and encode that both in the patch tokens that are generated from the visual transformer, or as well as actually the positional values that come out of it. Both of them can be encoded. So now, once we have that, we also want to look at what we are doing with our the appearance variant or clothing invariant branch, which is the modeling of the shape. Well, for the modeling of the shape, we can use the similar architecture that we built before. Again, the occlusion detection vector is something that we want to encode. So remember, the shape modeling is happening because we take an input image. We want to generate an encoding of the skeletal structure. That skeletal structure is nothing but a bunch of key points. Of course, they're connected. That's a graph representation of the skeletal structure. But fundamentally, we have these key points. What we want to do is actually use the occlusion detection in order to mask some of the key points. And by masking the key points, now we have a representation going into the decoder where some of the key points are missing. And what we would like to learn in the decoder is an ability to recover those missing key points. As a result, recover the shape, if you will, of the person in the presence of occlusions. And that's what we are learning as part of our shape model. So once we build that, well, now we want to actually combine the two. So we have an appearance numerical representation, a shape numerical representation. And what we build is an adaptive fusion layer where we run that through a convolutional layer and concatenate the 2 output structures that come out of that convolutional layer, of course, run it through another convolutional layer, and we eventually actually do a weighted summation of the 2, right? So convolutional structures are there mostly for us to be adaptive in the sense that if I have no occlusion, then I want to account for the shape as well as the appearance equally. If I have occlusions, I probably want to account for shape a little bit more than the appearance, especially depending on the region of the occlusion, right? So that's really what the adaptive fusion is learning, the weighting mechanism. Now, remember, we kind of had this ability to synthesize additional clothing. We have done that for a publicly available data set called PRCC. And by actually creating this augmentation of both additional appearance of clothing as well as all the occlusions, we extended that data set and what we call ePRCC, which is extended PRCC, which is now available in the public domain for other researchers to use and actually leverage this as part of the design of newer models. So that data set is open source and available for additional research. But what that has allowed us to do is now create a data set which has 134,000 images across 221 unique IDs, 3 cameras, and for each one of those IDs across 3 cameras, we have 6 clothing variations per ID, as well as all possible synthesized occlusion of the appearance of that person. So that is a much more richer data set that is available. There are other data sets available which don't have that extensive of a measurement, but they have, about 2,000 images, 200 IDs, single camera observation, no clothing variation information or occlusion information, right? But it definitely has occlusions. So these are examples from this occluded re-ID data set. You can kind of see that they have very large occlusions, right? You're missing half the person. The lower body of the person is not observable. The face or the upper body is covered or covered out, and so on and so forth. Now, when we build this model, what do we observe? One, explicit modeling of the occlusion actually does boost quite a bit the ability to do good re-identification. So the rank 1 accuracy on an occluded data set jumps from about 53%, which is what we had without occlusion modeling, to about 58%, right? It's a 5% increase in rank 1 accuracy. You actually get similarly about a 5%, 4.5% increase in mean average precision. For the occluded re-ID data set, right, the one that I showed you examples for, that also jumps up by about 10%, which is a significant improvement. You're getting about 87% rank 1 accuracy by explicitly incorporating the modeling of the occlusions. So all of this kind of leads to being able to generate more robust models. The performance in terms of inference time, so real-time performance, is also very scalable. We are able to achieve that in very short period of time. Now, what do we learn if we train a model like this? So here are differences in the attention map, right? So you can kind of see that if I explicitly model occlusion, all of a sudden, my learning is focused much more on the observable person as opposed to the car in this example. Similarly, in this example, I'm no longer learning from the bag in front of the person or the chair. It's focusing much more on the upper body, which is the observable part of the person, right? So our models are actually learning much better if we encode this information. And remember, our ability to encode a lot of this information gets better and better as we think about how we synthesize appropriate data that helps the model learn better. Similarly, in terms of shape representation, you can kind of see that our models are actually able to recover the geometry of the person, even in the presence of occlusions, right? So even though you have a lot of occlusion, you have bicycles in front of this person, actually the model is able to learn and recover the structure much better. Even in presence of occlusions where part of the body is missing, it recovers the structure. So this is great. So just to kind of talk about what did we learn, right? I mean, having, of course, a much better representation of the kind of variations we encounter and having a much better balanced representation of our data sets is impactful for learning robust models. More importantly, a certain amount of generative models can become targeted generative models for specific challenges that we face, can be very beneficial in improving the learning of the model as well as the generalizability capability of the model. I'll quickly wrap up with talking about, well, what's ahead, right? Well, this is great, right? But domain shift and generalizability is still a big problem for person re-identification. Oftentimes, these models will fail when we transition from one camera observation to another, from one city environment to another city environment. These are typically modeled in the domain shift. We still have to figure out how well we do this without necessarily having to collect data across every possible city or every possible different observation scenario. Cross-modal, multimodal matching is very important, right? So if I have observations, let's say from RGB cameras, as well as infrared cameras, can my models generalize across the two? Well, that's an open question and still being worked on quite extensively. More importantly, what about privacy and ethical concerns, right? So we are able to observe people. Well, the resolutions are quite poor, so we may not always be able to identify and actually recognize a person, right? But there are still those possibilities. So privacy and ethical concerns are important. How do we actually build these kind of models that are privacy preserving, right? So addressing those issues is also an ongoing challenge, an open challenge, if you will. Well, with that, I think I'll stop and maybe have some time for questions. Thank you.
Thank you very much, Dr. Shah. It was very interesting. I know you have a important meeting you have to get to at 1, so we need to have a short time for amount of questions.
I apologize for that. I got scheduled for a meeting and that was a little out of my control.
Yeah. I wonder, Dr. Embry or Dr. Trefalis, would you like to lead off with any questions or takeaways?
Yeah. One easy question, Shrash, is do you think there's been in the news lately people saying that they should ban public cameras because of identifying people? I know that goes in your privacy and ethical concerns. Do you have any comments?
Yeah, I mean, I think, it's very critical, right? So obviously, different scenarios matter. So I always say that, we benchmark a lot of the problems in this type of applications in terms of knowing how good we do, right? So when do we produce correct answers? But missing correct answers also has very serious implications. Certainly in these kind of scenarios, of course, in medical scenarios as well, right? So missing a diagnosis is just as problematic as or it should be even more problematic than making the correct diagnosis. So these are very important questions. So the question, for me at least, translates to how do we actually deploy these systems in practical scenarios, right? And if we deploy them in an automated scenario without human checks, which can account for other factors and other contextual knowledge that is not represented in these models, then that is the way these solutions should be implemented in practice. And that is an important part of the rolling out strategy. And we have had several setbacks for not just in this kind of scenario, but especially in biometric spaces. Where we talk about, person recognition problems and so on and so forth. We have had serious setbacks in those solutions design that work very well, but they got implemented and rolled out without appropriate human bound and checks. And that's very critical.
Thank you.
Thank you. I guess there's about 30 seconds for one last question. If anyone would like to unmute. If not, I have one very quick question, kind of fun, I think. Suppose someone wanted to subvert your system, to not be identified. What do you think the main issue with that, or the main method for that would be?
Well, so, obviously, so one thing you can hopefully you saw, right? I mean, a lot of this information has been captured. Certainly, there is some appearance information that's being captured, but there is also the body geometry that's being actually modeled, right? So anything that you do that will change that underlying representation, right? If I don't know, walk around with, 10 layers of clothing on me, that's going to alter my nominal body appearance. And, it's going to make the body shape look like not mine. So it increases the chances of the system matching that to someone else's. So yeah, I mean, very simple ways that you can actually, try to circumvent this. Now, of course, remember, it assumes that somehow I have knowledge of what information the system is using.
Right.
So, it's very interesting, by the way. I'll give you this little example, right? So I was working with some doctors, right? And they said that, the AI technology is progressing so fast that, they had some imagery, patient imagery, that they, uploaded into ChatGPT and asked some fundamental questions. And ChatGPT gave excellent answers to it, very, very good answers to it, right? And then, so we said, okay, wonderful. I mean, you're giving very accurate answers. So we asked ChatGPT, can you describe and break down exactly how you gave these answers in terms of what kind of processing did you do to give those answers? And ChatGPT actually came back and said, I'm sorry, I'm not allowed to give you those details.
Oh,
So, if you assume that you know what's happening, then yeah, you have a better chance of figuring out how to bypass it, right? But it requires us to know what is being modeled by the system like this.
right. Okay. Well, thank you for that response, and thank you for your presentation today. We won't hold you too long.
Well, I thank you again and really appreciate the opportunity. Please, if you have any questions, you have my email. Reach out anytime. I'm happy to answer any additional questions or there may not be even questions of this, just to brainstorm and love to hear more ideas. So thank you.
Thanks, Shishir.
Sounds great. Thank you.
Thank you.
And thank you everyone who's still in attendance for coming today, joining the seminar. With that, I think we'll end our presentation today so that everyone can